Okay, so on the screen you can see question 13 from last year's exam 2, the transformation that maps the graph of y equals cosine x onto the graph of y equals cosine 2x plus 4 is, and one of these matrices will map this onto this. To do this in reality, what you need to do is determine the transformations, and that's really the crux of what we're doing today, determining the transformations. There's a few ways to do it, but believe it or not, after kind of talking about function notation for the last few days, I actually find it much easier to use mapping than function notation to determine transformations. So let's get stuck into this, and hopefully we'll be able to answer the question that question 13. All right, so it's easy to find using inspection the transformation which takes y equals x squared to the graph of y equals x squared plus 2. That is, that this graph here would be translated 2 units up to turn into this. The transformations we find are only one possible answer. In fact, there are infinitely many choices. So this one here, you could translate 10 units up and 8 units down. You could do all sorts of things to it to turn it into this. Find a sequence of transformations which takes the graph of this to this. So this is one that I hope you can do via recognition. Okay, so what I'm noting here is that this will be a dilation factor 2 from x-axis. It'll be a reflection, so that's the 2 there, the negative reflection in the x-axis. It is a translation, 1 unit right, and a translation, 3 units up. But what if you didn't know that? What if you weren't able to pick the transformations by recognition that take this from this? So here's the method that I like to use. I call it the kind of serving it up on a silver platter for you. Okay, so these questions here, what I do is I write from y equals x squared to y equals negative 2 x take 1 squared plus 3. Now what I do is I call this getting this ready to pair. Okay, so I'm getting it ready to pair. That's my word. I don't even know whether it's right or not, but this is what I think. I'm going to pair this function with this function. All right. Now to do that, what I need to do is like pair x with x and y with y. And I can't pair it just at the moment because I've got this negative 2 and a plus 3 around the x. So what I'm going to do is I'm going to rewrite this as y take 3 over negative 2, noting that this and this are our images. So this is y dash equals x dash take 1 squared. And that's still just y equals x squared. Right, now what I do is I then go, all right, I'm going to pair y with this. So y equals y dash take 3 all over negative 2. And I'm going to pair x with this. So x equals x dash take 1. All right, now what I'm really after is I want to get this stuff here. I want the mapping, all right, because once I get the mapping, I can just read it off and they will be the transformations that take the original to the image. So really what I want to do is find out what x dash is and y dash is and pop it there. So the aim of the game will be to make x dash the subject. Okay, so note that this is different from what we've been doing. We've been making x the subject. Negative 2y plus 3 equals y dash. Right, let's pop those in. We've got x plus 1 and we've got negative 2y plus 3. What we can do is we can simply read off the transformation. So I can see here that this is a translation 1 unit to the right, and there it is there. I can see here that this is a dilation factor 2 from x, and there it is there. I can see this is a reflection in the x-axis, that's there. And I can see that this is a translation 3 units up, and that's there. So these transformations here are the ones that I got from recognition. That's really good because if I actually can't recognize the transformations, then I can just use this method here to kind of, this is again what I call, this is like the silver platter. Okay, this serves it up to you. So you don't have to be like, oh, I think it's this, I think it's this. It's just like, bang, here it is. All you have to do is read it off. All right, so this one here is one where if you said to me, how do I take that truncus to this truncus? Now I can sort of see a few of them, like it's a dilation factor 5 from X, but because of the negative here and the plus there, I know it's like a translation 2 to the right or 2 to the left, it's a reflection in the Y, but I'm also not 100% about the order, all right? So that's a problem. All right, so again, what I would do to make 100% sure on this is I would absolutely do this via mapping. Okay, so again, you need to have some flexibility with transformations. You can't be all function, or you can't be all all mapping. You got to sort of combine both of them. That's my belief anyway. So I write from y equals 1 on x squared to y dash equals 5 on 2 take x all squared. That's x dash. Okay, so what I do is I get it ready for pairing. Now I need this is 1 on x, this is 5 on x. So what I'm going to do is I'm going to go y dash over 5 equals 1 over 2 take x dash all squared. Okay, now this is again where I say this is ready for pairing, but like don't sort of be throwing that around to your maths tutor or something like that and saying pair them up because that's not really official maths talk, it's just what I think or what my brain thinks when I do this. So y dash on 5 equals y, x equals 2 x dash. All right, now remember what we did last time was we wrote out x comma y maps to x dash, y dash, where these are the transformations that take the original to the image. All right, so what I want is the image as a subject. So I'm going to go x dash equals x take 2, x negative x dash equals 2 take x. All right, so I can pop that in to take x. And this is going to be y dash equals 5y. There it is there. Okay, so now what we can do is simply read these off. Now, I'm not really happy with the way they're written, so I'm just going to change that quickly to negative x plus 2, comma, 5y. All right, so let's read off the x's and then read off the y's. So I'm going to go reflection, so that negative sign there at the front of x is a reflection in the y-axis. That is a translation 2 units, right? And this is a dilation factor 5 from x-axis. Okay, so good time to just experiment a little bit here. So I'm going to define f of x equals 1 over x squared. All right, and what I'm going to do is run these transformations. Okay, so I'm just going to start with my function here. So all I'm doing is I'm testing these transformations to see whether these produce this function here. Okay, so starting with f of x, okay, what I'm going to do is produce g of x equals, so reflection in the y-axis is f of negative x. G h of x equals, translation 2 units to the right is f of negative x. Take 2, almost wrote plus 2 there. So x take 2 gets dropped in for x. And dilation factor 5 from the x-axis is k of x equals 5 times f of negative x take 2. So you can see here, running the transformations going from this to this using the function notation, because I'm really good at using function notation for that. Okay, so f times 5 times f of negative x take 2 and open, open, close, close. See what happens. Okay, that's interesting. So that actually is that function there. Okay, so I am actually right, although I should have probably done this before I did the example, but this is good, and this is what would happen in class. You'd see me thinking about this. So I've looked at this and looked at this, and I've gone, oh, well, oh, I must have got the transformations wrong. But actually, let's write f1x equals 5 over, and what I'm going to do is just factor out this negative here in the denominator. So I'm going to go negative 1, x take 2, close brackets, open brackets, close brackets, all squared. It's really the same thing. Is all I've done is I've got the x take 2 here, factorized it, but kept it all in this bracket here, meaning it's all squared. Now, if you remember, this is just some Year 9 indices here. X, y squared is the same as x squared, y squared. And I can do or use the same idea here, which is 5 over. Now I square the negative 1, which means that the negative 1 becomes 1, and I square the x take 2, which becomes simply x take 2 all squared. So that function there and that function there are exactly the same. Okay, find a sequence of transformations which takes this to this. All right, so again, I've got absolutely Buckley's chance of getting this right if I did it, so I'm going to use the mapping approach for sure. Okay, so here goes. I'm going from y equals 3 on x take 1 all squared plus 6 to y equals 1 on x squared, where this is the image. Okay, so let's get them ready for pairing. This time around, the second function, or the one we're going to, doesn't need any work. The first one does. So we've got y take 6 over 3 equals 1 over x take 1 all squared to this. All right, so let's pair them up. Y take 6 over 3 equals y dash, and x take 1 equals x dash. All right, now remember what we do here, x dash, y dash, transformations go there. So the original comes in, we do this stuff, and it creates the image. So what stuff is it? To create x dash, it's going to be x take 1, i.e. this time around there's no algebraic manipulation that's required. Y take 6 over 3. All right, so now that we've got this, all I do is I read the x transformations first. You can do them in any order. You can read the y transformations first, then the x transformations. That's fine as well. So it's the dilation, no, it's not. It's a translation. 1 unit left. Now, starting with y, we're going to go 6 units down, so translation, 6 units down, and it's a dilation 1/3 from x-axis. Now, a really good thing to do would be to write those transformations in function notation, slam them into a defined version of this function here, and see whether indeed it produced the y equals 1 on x squared graph. That'd be great, because then you'd be like determining the transformations, then testing the determined transformations, and really going around in circles and really testing out your knowledge. So that'd be a really good thing to do. Right, this is a little edit of the original video here, because I actually did stuff this problem up. So I'm just popping this one in. So if it looks like it's a different sound or different looking image, yep, confession time, I stuffed up. All right, so state the transformations that map this to this. So we're going from y equals root x to y equals negative root negative 5x take 3 all over 4 plus 2. So that's dash and that's dash. Okay, now what we'll do is we'll get ready to pair these up. So I'm going to subtract 2 and divide by negative 1. So that's going to be y dash take 2 divided by negative 1 equals, now this one here I'm going to expand out this. So I'm going to get rid of this negative sign here. So I'm going to rewrite this as 3 take 5x all over, so root the top, root the bottom means the bottom rooted is 2. Right, now I'm going to multiply by 2. Right, and now we're ready to pair these up. Now, you could have left it at this point here and had the whole thing rooted and then paired it up then, but I just wanted to clean it up first because it probably means that the transformations will be read off a little bit easier. Okay, but it's not compulsory to do that. Okay, so y equals negative 2 brackets y dash take 2 and x equals 3 take 5 x dash. All right, now x comma y, that's 2, x dash and y dash. They're the transformations that take these to the images. So I need to make x dash and y dash the subject. So I'm going to go y over negative 2 plus 2 equals y dash and pop that in. So I'm going to write it as negative y over 2 plus 2. So I've just grabbed that negative and popped it on the top. Okay, x is going to be x take 3 all over negative 5 equals x dash. And I could pop it in like that, but I would prefer to write this as negative x plus 3 all over 5. That is, factorize out negative 1 there, and then divide the negative by the negative. All right, equals x dash. So that's going to be negative x plus 3 all over 5. Okay, so now what we'll do is we'll read off the transformations. So I'm going to start with x and say that the first thing is the negative. So that means that there is a reflection in the y-axis. Then 3 is added to it. Okay, so it is a translation, 3 units to the right. And then it is a dilation factor 1/5 from the y-axis. Right, so they are the transformations from the x-axis. Right, and now to the y transformations. So it gets negated first of all. So this is a reflection in the x-axis. It is a dilation factor from the x-axis and a translation 2 to the right. Up rather. Okay, so there's my set of transformations. Now, mind you, that is not the set of transformations, that's a set. Okay, so what if you wrote x dash as something different? So what if you wrote it as this one here, which is x take 3 all over negative 5. And let's just play around with this one here. I'm going to make a common denominator. So that's going to be 4 on 2. This is negative y plus 4 on 2. So that is still exactly the same as that, where we've got negative y on 2 plus 2.
Now what you would do is note that the transformations you would say would be 3 to the left, reflection in the y-axis, and a dilation factor 1/5 from the y-axis. So you're going to get your translation first and your reflection second. So the order of those will be reversed. Okay, dilation factor still. Now this one here, it'll be a completely different set here. So we've still got reflection in the x-axis. And what we're going to do is translate first. We're going to go 4 up, so 4 units up. And then what we would do is dilate by a factor of half. So these would go around the other way. And that would be a completely different set of transformations, which would still be correct, okay? Because this expression is the same as this expression, and this expression here is the same as this expression. So anything that's true is perfectly allowed, okay? One final one, I mean, if you want to get increasingly complex, you can do this. Negative x on 5 plus 3/5, comma, negative y plus 4 all over 2. So what we could do here is note that this here, all I've done is divided by -5 and divided by -5, which would be reflection in the x-axis, dilation factor 1/5 from, reflection in the y-axis, dilation 1/5 from the y-axis, and then a translation 3/5 to the right. Okay, so again, because they're equivalent, that would be an equivalent set of transformations. It wouldn't look exactly the same as these, but your transformations would be correct. So the moral of the story, girls, is that you've got to be good enough to know that if you've made some algebraic moves, that if you're checking your answers and you're seeing whether you did a correct transformation, that yours may well be correct. Okay, and just go back and look at your algebra, okay, and try to generate the transform function from the original to the image by using your transformation techniques and see whether this function ultimately does pop out at the end.
Okay, so this one here, remember this one written by Ms. Cowan, it was a beautiful question. So from the circular function set, state a sequence of transformations which takes this to this. Okay, so we're going from y equals 3 sine 4x to y dash equals -4 sine 2x plus 6, take 2. That's the dash. Okay, so let's get ready to pair. Y on 3 equals sine 4x, going to y dash plus 2 over -4 equals sine 2x dash plus 6. Okay, y on 3 equals y dash plus 2 all over -4. 4x equals 2x dash plus 6. Okay, so remember, x comma y maps to this stuff here takes us to our transformed or our images of x and y, the images of the originals. Okay, so this tells us that I need to make x dash the subject and y dash the subject. So let's do that first. So this one here, I'm going to multiply this by -4. So I've got -4y over 3, take 2 equals y dash. -4y over 3, take 2. And this one here is going to be 4x take 6 on 2 equals x dash. Just have to tidy that up a little bit. That's 2x take 3 equals x dash. So what I did was 2 went in and 2 went in. So I've got 2x take 3 equals x dash. Okay, so let's state them. Starting with x, it is a dilation factor 2 from the y-axis. This 3 says a translation 3 units left. Okay, we've got a reflection in the x-axis. It is a dilation factor 4 on 3 from the, which one? Dilation factor in the x, isn't it? Yes. There's dilations from x change y. Dilation factor 4/3 from x axis, and this -2 here is a translation. Excuse the handwriting, everything's gotten worse as this one's going on. Translation 2 units down. Okay. All right. So job today, get 3E done.